In section 9.4, we're going to address 4 objectives. It's going to be numbers 13 through 16. And what we're going to be doing is logarithms still, but we're going to be looking at natural logarithms. So 13, we're going to compute values using compound interest formula. 14, we're going to use the continuous change formula. 15, we're going to graph base E exponents and find the graph of their inverses, which is called natural log. And then 16, solve problems that arise from exponential or logarithmic models. So let's go ahead and do that. The first objective talked about using the compound interest formula, and this is it right here. What you want to remember from that is the P in here is our initial amount that we put in. A is your kind of ending amount, so you might want to have starting amount, ending amount. The R is our rate. T is our time. And then N in this case is how many periods per that time. So it's normally N is how often it's compounded. So how often something is compounded. And an example would be if they say it's compounded quarterly, monthly, daily. So you would adjust for that. So let's go ahead and take a look at this problem here. Here they're saying that we're going to put P dollars into an investment for 1 year at 100% interest. How much will we have after a year? So how much will we have after the year? That is our ending amount. P is our starting amount. If it's 100% interest, it's going to be 1 plus. 100% is going to be written as a decimal, so what you would do is move the decimal place twice, so you're going to have 1 in here. How is it compounded? They're not telling me, so I'm going to say N. It's going to be the power of our time is 1 year. And again, I don't know what the N is. They didn't tell me if it's going to compound daily, monthly, or what have you. Now, what I want us to do is use this particular formula. And on the next slide, we're going to fill in what if it's compounded where N is 1 versus where N is 2 and where N is 3 and so forth. And you want to think about this in terms of a year. So if N is 1 here, it means it's compounded once a year. If it's 2 in here, it's going to be compounded twice a year, so every 6 months. If it's 3, it's going to be compounded every 4 months type of thing. So if we put $1 in the bank and we get 100% interest back, I want us to go and look at how this formula changes for different values of N. So let's go ahead and look at the next slide for that. So if we take the formula from the previous slide and we're saying that we're going to put $1 in the bank. Again, this is $1 in the bank at 100% interest. And if we do it once a year, what we would do is just say A is going to be equal to 1 times 1 plus 1 over 1, 1 times 1. What you're going to get is, looks like this, is 1 times 2 to the first power. The answer is $2. So you put $1 in, you get 100% interest back, so they completely double it, so you're going to have $2. Now, what if they compute interest twice a year? So every 6 months they're going to compute interest. They hit this button, give you the interest for holding their money. And if you do that, the formula just to set it up would be A equals 1 times 1 plus 1 over 2 times 1 times 2. And so what you're going to end up getting when you multiply this through is $2.25. Now we're going to do that when N is 4, 6, 12, and so forth. I'm going to pause the video and show you the answers real quick to what you get. If you take a look at the results, you're going to notice when you get down to the very bottom here, what if they compound the interest 365 times a year? So that means every day. At the end of the day, they compute the interest on $1, put it back into your account. The next day, compute the interest on that $1 and a couple of cents and so forth. And if they do that, we're going to get in terms of money, it's roughly $2.72. You know, what if they did it every hour? What if they did it every minute? What's going to happen to this case? The question is, again, if they did it every second even, will this number get extremely high? Will it work its way to $3, $4, or $5? Let's go ahead and look at the next slide in terms of what if it's compounded every hour, minute, or second. If you do that with this formula, again, just notice how we've changed it. This is the one that we already did, and we got that the answer was this. it was 2.71, and I'm going to go out a few more decimal places here. If you do it every hour, every minute, or every second, what you're going to get is this number here. You're going to notice it seems to be stopping a little bit. And what it does is it approaches a certain number. If it were to compound every second, and they hit the button every single second and give you interest, you're only going to get almost $2.72. That really is not a big change from what we had here. Back on this one, when we did it every day versus every second, the change is very, very small. And what it is this sequence right here that we've looked at, this formula, if you put even a bigger number than 31 million in there, it's going to approach the number 2.71828 and so forth. And there's actually a number for that. The number is called the letter E. It's very similar to pi. How pi is approximately 3.14159 and so forth. E is also a number. And if you go to your calculator, you can find it. On the calculator, the E button, it's right above the natural log button. So look at the number 4 and look over to the left. What you're going to want to type in is you can type in E to the first power, and you're going to get that the number is 2.718281828 and so forth. Okay. And this is called Euler's number, named after Leonhard Euler here at the right. Now, why do we care about E? We care about E in this sense. E is used to do exponential models of this nature where there's continuous change. So if something is not compounded daily, weekly, or monthly, it can be continually compounding. There are things out there in the world, for example, that have a decay model to them. And they don't decay every day. They don't decay every month. They continually decay throughout their life. A good example would be something that's dying. After something is dead and decomposes, it doesn't sit there and just start to decay like every single hour. It's just continually doing that. And it's a continuous change model. So what we're going to use is a different formula. We take a step away from this formula, which is compounded at a certain time period, and we use this one. It's A PERT. You take A equals P, just as we had before, right here, and we still use the T, but you use E to the R power. So if you're doing a problem going forward and they say something's compounded continuously, you go ahead and you use this formula. Let me show you the difference on how they work in the example 2. This will show you the difference quite easily. Suppose $500 is invested in an account paying 8% annual interest rate. Okay, fine. So we have our P is our starting amount of $500. The rate is 8% as a decimal is 0.8. All right. Part A, give the balance after 4.5 years if it's compounded continuously. Part B, how does this compare if it's compounded quarterly? So the continuous compounding is A PERT. The compounded differently would be this time period. So let's write this down. Okay. A PERT, you would just put in how much am I left with is A. If I put $500 in, it's E. Our rate is 8%, and to the time period here is 4.5 years. If you put this in your calculator, you're going to want to raise E to the power. This actually becomes a 0.36. And then go to the calculator, and again it's to the left of the 4, so do second natural log, or you do E to the 0.36 power. You're going to get that answer and then times that by 500. You should get that the answer, there's going to be $716.66 if it's compounded continuously. Now, what if they compound it quarterly instead? Fine, come into this other formula. A equals $500, 1 plus my rate of 0.08, divide it by quarterly, so that's 4 times a year, and times it by the time period we're saying here is going to be 4.5 years. But in that 4.5 years, they're going to hit the interest button 4 times a year, so times that by 4. When you simplify this properly and check your order of operations, you're going to get approximately $714.12. There's not a big difference, but there is a slight difference in the compounding method and the answer for that. Now let's take a look at this slide. It's more of a vocab. When they talk about annual yield, if they ask you what the annual yield is, that's typically the interest rate. So when we look at the same example here, the 8%, you might say, oh, the annual yield is 8%. But if they compound this thing continuously, or even if they compounded it quarterly, you're going to get a little bit more than 8% because they hit the button for interest more than just once a year. So what you want to do is figure out what is the actual percent. Let's go back and look at it for the compounding continuously formula. Again, I like to just say A pert, where R and T are the exponents. And we're going to put the $500 in. E, we have 0.08. And if you do it the time period is for 1 year. If you put that in there, what you're going to get is 500 times 1.083287. Now this looks just like the old formula that we used to deal with, right? Where we had A equals P, 1 plus or minus R to the T, the exponential growth or decay function. Remember, under growth and decay, this right here was called the growth or decay factor. In this right here, that component was the actual growth or decay rate. That's the annual yield that we're going to see. So when you look at this formula, this is the growth factor because it's greater than 1. But what's the actual percent? It's this number right here written as a percent. So it's really 8.3287% is the actual yield on this investment. You can easily answer part B, what is the value of this investment? Just simplify this and you're going to get $541.64 is the answer. Okay. If you wanted to, you could figure out the increase another way. You could take the 541.64 and divide it by the initial $500. So if you were to take this amount, divide it by 500, you're going to get 1.08328, and from that you can actually get the actual annual yield from there. We only have a few more slides left on these notes. The next two are about the graphs, and then we'll wrap up with the word problem and be done. This graph is not too hard to see. We're just going to sketch it here. What they've done for us is they took the good old-fashioned, compound monthly quarterly formula, and they've set it up for us. This is if it's compounded twice a year, 4 times a year, 12 times a year. And they did a graph, so you can kind of see what it looks like. And then they sketched what if it's continuous, the compounding continuously. That's this graph right here, folks. Y equals e to the x power is an exponential equation. You might be used to looking at these exponential equations, 2 to the x. This is e to the x. What it is, it's an exponential function with just base e. Remember that e is approximately 2.7 and so forth for numbers. So when you sketch it, what you're going to see is y equals e to the x power is actually going to give you this blue graph right there. Now, this is the equation format. This is the function format. Remember, f of x just means y. This is notation for the word inverse. So it's shorthand for inverse. They want us to find the inverse of this function. Fine. To find any inverse, all you take is the x and y and you change them. So instead of y equals e to the x, it's going to be x equals e to the y. Now to graph this, what you would do is rewrite it to solve for y. So now that we do this, what we're going to do is we can just rewrite any exponent as a logarithm. So what I'm going to do is start with the base. So this is log base e of x equals y. Log base e of x equals y. And that is going to be the inverse of the function. Okay. Let's look at the next slide on what this looks like. This graph is a nice picture of just y equals e to the x. So we looked at this on the last slide. Now remember, inverses is when we said you change y and x. So this is the line y equals x. What you should see is when you graph the equation we found, and this is what we found, was y equals log base e of x. When you graph that, you should get the red curve here. So you're going to see a nice flip over that green line. Well, you might want to find where log base e is. In your calculator, the log button is log base 10. So right beneath the log button on your calculator is the natural log. This right here is exactly the same as this. They have a specific button for log base e. It's the natural log. So if you go to your graphing calculator and you do y equals the natural log of x, you will get this red curve right here. I'm not going to talk about the domain and range of this. You can look at the function and determine your own domain and range. It's not hard to tell. The range on this will be all real numbers. The domain on this is going to be all the numbers greater than 0 for this particular example. But it's going to vary in terms of domain and range based on where the graph sits on the actual grid paper. So let's go on to the very last example, which is an application of using natural logs. All right, here we go. Under certain conditions, the height h in feet above sea level can be approximated from the atmospheric pressure P in pounds per square inch, which is called PSI. It's what you use to check the pressure in your tire. You can do that using this equation right here. Okay, so it has natural logs in it. Human blood boils at 0.9 psi. In such a situation is fatal. At what height above sea level will blood boil in an unpressurized airplane cabin? Okay, they're telling you that it boils at 0.9 psi. And we know that the P in this equation is psi. So just plug it in. At what height are you? Well, the height is the natural log of 0.9 minus the natural log of 14.7, and you divide it by this. So don't overcomplicate this, just do order of operations. Be careful, you must do this first half first. Do all of this first, take that answer, and then divide by this number. When you do that, you're going to get that the height is 71.621, and we're talking feet above sea level. So when you're 71.621 feet above sea level is when your blood will boil and basically you would die. Not the most pleasant problem, but a good one of how natural logs are used. And by the way, natural logs are used in a lot of science problems because the letter E, or the number E, happens naturally in the world more than you would expect. And so the application really does show up in the science field quite a bit. The only adjustment to the homework I would make is you can go ahead and skip number 15. That's it.